Carnot engine and refrigeration cycle. Carnot engine is nothing but a heat engine, where it is taking some heat from the hot reservoir, performing some work, rejecting some heat to the cold reservoir. System is a cyclic process. System comes back to the normal state. Normal petrol engine and diesel engine has got very low efficiency. Heat engine concept is it is taking some heat energy from the hot reservoir without changing its temperature. By taking the heat energy, temperature of the system does not change. You take a hot water in a tumbler, you pour it in the well or pour it in the lake. The temperature of water in the lake or well does not change. That is atmosphere. By adding an extra heat to almost nil quantity, the temperature of the system does not change. You take a hot coffee, keep it outside. After a few minutes, it becomes to room temperature. Atmospheric temperature will not increase its temperature. Atmospheric temperature will be normal only, around room temperature. So by taking heat from the hot coffee, the system temperature does not change. That is a major difference between normal petrol and diesel engine. So the heat engine, what we are going to discuss, that is a basic principle in Carnot. So QH is the amount of energy taken from the source. Work done by the system is W. QL is the amount of energy rejected to the sink. High temperature, low temperature. Energy taken from the source. Rejected to the sink. So what is the work done here? QH minus QL. Amount of energy taken from the source minus amount of energy rejected to the sink. That remaining will be the work done. Okay. Efficiency of heat engine. Generally, efficiency means work done by the system divided by what energy you are giving to the system. You are giving to the system is QH, amount of energy you have taken from the source. So W is QH minus QL by QH. So you can write efficiency as 1 minus QL by QH. Correct? So keep this principle in mind. We are going to proceed with Carnot engine. Heat reservoir. Cold reservoir. Working substance, that is heat engine, perform some work. So heat energy, what you are giving to the system, taking from the system is QH. Some energy rejected to the sink, so-called sink. Work done by the system is QH minus QL. So this is the principle of Carnot engine. Okay, keep this in mind. We'll proceed with four different stages. Four different stages of Carnot engine we will take. Before going to the four stages, what are the components used here? First one, the source. Amount of energy taken from the source is TH. It is a hot source. Any amount of heat you can take it from it without changing its temperature. Non-conducting stand. Non-conducting stand means non-conducting platform. It has got non-conducting platform. Then you have a reservoir, frictionless piston in a container with some gas. Frictionless piston. You can compress the gas or expand the gas, depending upon isothermal process or adiabatic process, compression or expansion. We will discuss. Working substance, the gas. There are four stages in this Carnot engine. Isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. Four stages. In these four stages, after finishing this, what is the work done by the system? What is the efficiency? We are going to calculate. So it is nothing but a heat engine working in cyclic process. System comes back to the normal state after different stages. That is known as cyclic process. First stage, isothermal expansion. Keep the working substance, that is frictionless piston in a gas in a container, on the source. Keep it on the source. Allow it to expand isothermally. When you allow it to expand isothermally, already we have learned, in isothermal process, pressure and volume of the system changes, but temperature remains constant. Pressure and volume of the system changes, temperature remains constant. That is called isothermal process. So, PV changes, but temperature is a constant. QH is the amount of energy, heat energy taken from the source. When you keep the working substance, that is gas in a container with a frictionless piston on the source and allow it to expand isothermally, what is happening? Pressure decreases, volume increases. Since it is isothermal process, otherwise we call it as quasi-static. Quasi-static means slow process. Temperature remains constant. So in the graph between pressure and volume, expansion means pressure decreases from this point to this point. Pressure decreases. Stage 1, volume increases from here to here. P1, V1, temperature TH changes to P2, V2, same temperature TH. First stage. Second, So this is the work done. This area, if we calculate, that is the work done. But we know the formula for work done in isothermal process. What is the formula for isothermal process work done? W is equal to basic formula for isothermal process work done. We have learned mu RT log V2 by V1. Mu RT means in our case TH. This already we have derived. Work done in isothermal process. Number of moles we call it as mu or universal gas constant. TH constant temperature. V2 V1 final volume initial volume. So point A, point B, point M. This is second stage. In second stage, adiabatic expansion. So in adiabatic expansion, keep the working substance on a non-conducting stand. Non-conducting stand means non-conducting platform. Already we have learned adiabatic process means temperature changes. Expansion means temperature decreases. Compression means temperature increases. Because adiabatic means nothing is constant. Expansion, that is basic. Pressure decreases, volume increases. Expansion, adiabatic, so temperature decreases. So stage 2, this point, P2, V2, it changes to P3, V3. Temperature also changes from TH to TL. Second stage. So P comma V changes, but temp changes. Temperature decreases to TL. From TH, temperature decreases to TL. This is a work done. This area, if we calculate, that is a work done. But adiabatic process work done, we know the formula. What? Work done. Second stage. What is the formula for adiabatic work done? Already we have learned. Basic formula, adiabatic process. Mu R, gamma minus 1. Gamma is ratio of specific heat capacity of gases. Gamma, ratio of specific heat capacity of gases. Cp by Cv, that value. Mu R gamma minus 1 into final temperature minus initial temperature. Actually, 1 minus gamma, the basic formula is 1 minus gamma final temperature minus initial temperature. When you write gamma minus 1, negative sign will come. So we are putting TH minus TL. Actual formula, mu R 1 minus gamma final temperature minus initial temperature. Final is TL, initial is TH. We are changing 1 minus gamma as gamma minus 1. So this is also changed. This is stage 2. Stage 3, adiabatic compression. Isothermal compression, stage 3. Keep the working substance on the cold reservoir, that is so-called sink. Any amount of heat you can reject to the sink or reject to the cold reservoir without changing its temperature, because it is isothermal. Compression basic formula, you know what? Pressure increases, volume decreases. Whether it is isothermal process or adiabatic process, compression means pressure increases, volume decreases. Expansion means volume increases, pressure decreases. That is constant. And isothermal process, so temperature remains constant. So from this point C, this is the point D, it changes. See here, pressure from this point increases. Volume previously it is here, now it has come down. G. I, J, K. Any number you put, no problem. Any letter you can represent. It is only a representation. So stage 3, C to D, pressure increases, volume decreases, temperature is a constant at TL. So this point is P4, V4, TL. Temperature remains constant. Formula, work done. Stage 3, isothermal process, mu r, TL, logarithm. What is happening? V4 by V3. V4 is here, which is less than V3. So we have to put a minus sign here. It will become V3 by V4. Volume decreases, ma'am. From V3, it has decreased into V4. N point. Now it is G point. Volume decreases. So minus sign. Okay. Right. This is stage 3. Stage 4. Adiabatic compression. Keep the working substance again on the non-conducting stand. Gas with a frictionless piston in a container. Keep it on the non-conducting stand and compress it adiabatically. When you say adiabatically, process is quick. So what will happen? Temperature increases because it is compression. Pressure decreases, pressure increases, volume decreases, but temperature is not a constant in adiabatic process. So temperature also changes. System goes back to the original state, A. So pressure and volume changes. Temperature increases to TH. Here the temperature is TL. Here the temperature increases to TH. Work done. Fourth stage. Formula mu r 1 minus gamma final temperature minus initial temperature. Final is TH, initial is TL. So I can write TL minus TH. When you replace this, it becomes gamma minus 1, TH minus TL. Here work done is negative. Why negative, sir? Why minus sign here? Work done is negative. Work done on the gas. Work done by the gas means it is plus value. Work done on the gas. You are doing some work. Expansion means work done by the gas. On the gas, minus. Okay. When you compare second stage and fourth stage, these two are equal and opposite. These two nullifies. So work done by the system means it is Q1 amount of QH amount of energy taken from the source. QL amount of energy rejected to the sink. So work done is QH minus QL. That's what we have proved. This is cyclic process. Sir, I don't want this formula and all. I want to express it graphically alone. You can express, no problem. Stage 1, isothermal expansion. What you have done, A to B. What area here? A, B, M, K. Shade this area. Work done in graphically means area A, B, M, K. Stage 2. Work done. It is starting here, ending here. So BCNM area BCNM. Stage 3 work done. From C it has come to the point D. So CNGD. Work done. Stage 3 area CNGD. And finally, it is a cyclic process. System comes back to the normal state. A, point A. Starting here. DGKA. Area DGKA. Correct? So this is stage 4. You can express mathematically or you can express graphically the work done by the system. Okay? Fine. Now, so pressure and volume, you have drawn the graph for a cyclic process, isothermal 2 stages, adiabatic 2 stages. So work done by the system W is equal to stage 1 minus stage 3. Stage 2 and stage 4 equal and opposite, it nullifies. So stage 1 work done is QH amount of energy taken from the source or hot reservoir. QL is the amount of energy rejected to the cold reservoir or sink. QH minus QL is the work done by the system in the heat engine by Carnot engine concept. Efficiency eta. What is the formula for eta? Heat energy taken or given to the system, that is maximum QH. Always efficiency means denominator will be the maximum. Numerator is the work done, that is W. So I can write QH minus QL by Q. So QH by QH, eta is equal to 1 minus QL by QH. Correct? 1 minus QH by QL. Correspond QL by QH. Corresponding temperature, if you want, I can write 1 minus TL by T. From the efficiency formula, basically you can understand TL is less than TH. So definitely efficiency is less than 1 or less than 100%, because no engine can have 100% efficiency. It is impossible. Every engine or every concept has got some deficiency. Some energy will be wasted. So efficiency of Carnot engine cannot be 100% because reservoir, cold reservoir temperature is less than hot reservoir. So this is less than 1. Less than 1 means 1 minus say 0.9, 0.1, 0.2. Anything you take, definitely it is not 1. It is not 100%. Correct? Fine. One more concept also you can discuss here. What is that? TL. You can ask, sir, TL is 0 and TH is infinity. Then I will get efficiency is 1 or 100%. TL cannot be 0 Kelvin. No temperature can attain 0 Kelvin, sir. 0 Kelvin is absolute 0. Absolute 0 is unattainable. So you will never get 0 Kelvin for the cold reservoir. 0 degrees Celsius is different. You should not get confused here. 0 degrees Celsius is different. 0 Kelvin. 0 degrees Celsius means 273 Kelvin. 0 Kelvin is impossible. That is called absolute 0, not possible at all. TH cannot be infinity. Sir, 1 by infinity is 0. That is also not possible. All temperature is measurable. You cannot have an infinite temperature. Temperature of sun itself is measurable, sir. Sun temperature is what? 14 million Kelvin photosphere temperature. 14 million Kelvin is measurable. So you cannot have infinite temperature here. So TH cannot be infinity. TL cannot be 0 Kelvin. Therefore, efficiency of Carnot engine cannot be 100%. Always it is less than 100. Okay. So this is a perfect heat engine basic example. So first part we have finished. Carnot engine. Second part will go for refrigeration cycle or refrigerator. Refrigerator is a reverse of heat engine, reverse of Carnot engine. Why you call it as reverse of heat engine or reverse of Carnot engine, sir? What is a refrigerator does? What work it is doing? When you give some substance inside the refrigerator, it is becoming cold. That is the work done by the refrigerator. Heat engine, some energy is taken from the source, some energy is rejected to the sink. Whereas in refrigerator, it is reverse happening. Hot reservoir. Hot reservoir means your room only. Where you have kept the refrigerator? In kitchen, in the hall. I have kept the refrigerator there. So that is known as hot reservoir, room temperature. This is refrigerator inside of refrigerator. Using a compressor, it is taking energy from the compressor, cooling the substance, and some heat is rejected to the surrounding. Surrounding means atmosphere. So energy taken from the refrigerator, from the compressor is it is taking. Energy rejected. So QL amount of energy taken, QH amount of energy rejected. So this is the working substance. Refrigerator inside, this is the refrigerator. Actual refrigerator. QL minus Q. What is the meaning of QL minus QH, sir? Generally, low temperature, high temperature. Work done means it cannot be QL minus QH. You are taking some energy, means that is cold. Definitely that value is less. So minus sign should be outside. So work done by the system is QH minus QL. Why minus sign outside? Means you are taking some energy from the cold body. Correct? QL minus QH. QH minus QL, you need not put negative sign because hot body minus rejected some energy to the cold body, you need not put minus sign. The work done by the system is QH minus QL. Same thing we have done in Carnot engine, sir. Carnot engine, you are taking some energy from hot reservoir, rejecting. You are taking energy from the cold reservoir, rejecting to the hot reservoir. Hot reservoir means in this case it is not hot body, it is the surrounding. Backside of a refrigerator, if you see, it is slightly warm. Inside it is cold, ma. Backside of a refrigerator, you can see some grill is kept inside. Backside, which dissipates the heat faster. Always you have to keep the refrigerator in a corner. Backside of that, one window is there, means it is safe. Easily that energy will go to the atmosphere. Suppose that closed system, there is no window nearby. Backside not necessarily, nearby. There is no window means that temperature will take some time to go to the atmosphere. So, in the case of refrigeration, it is not efficiency here. It is coefficient of performance. COP. Coefficient of performance. What is the case of coefficient of performance here? Represented by beta. QL by W. QL means quantity of heat energy taken from the cold reservoir. Using compressor, some energy is taken by the system. This is work done by the system. Beta is equal to QL by QH minus. So I can write in terms of temperature TL by TH minus TL. There you have TL, TH in refrigeration cycle. You have 1 minus TL by TH. That is TH minus TL by TH. In Carnot engine. So definitely some relation should be there between these two. You simplify. Final formula you will get beta is equal to eta by 1 minus eta. Definitely 1 minus eta is less than 1. You will get beta value more. Eta, efficiency of heat engine, Carnot engine in our example. Beta is called coefficient of performance of a refrigerator. Correct? Two important points I want to discuss here. Beta should be more. Beta should be more means TL should be more. The TL is a temperature you are taking from the compressor, which is the basic concept of the refrigeration. TH minus TL should be less. This one you cannot do anything because this is the refrigeration. But this I can keep. TH is what? The body temperature. You are keeping some substance inside the refrigerator. The temperature should be less. Then denominator TH minus TL will be less. Denominator is less means total value is more. Performance will be excellent. Increased value. What is the concept, sir? What is the meaning? If you want value more for beta, simple example, milk in a container. After you have consumed the milk, you are keeping the remaining milk in the container. Allow the hot milk to become normal temperature, room temperature. Then you keep it inside the refrigerator. TH 30 degree minus something. That is better than 60 degree minus something. TL value is fixed, you cannot change. Say 10 degree. 30 minus 10, 20 degree. 60 degree hot milk I am keeping. Sir, anyhow it is going to reduce the temperature. It will take more time. You are giving more work to the compressor. Compressor efficiency will be reduced. Overall, the performance of the fridge will be reduced. So never keep hot substance inside the refrigerator. Allow it to become normal outside itself. Then you keep it inside the refrigerator, it will become cold. Do you understand what I am talking? Hot, suppose 100 degrees Celsius, water, boiling water. You have taken some water, allow it to cool in the outside refrigeration itself. Just to keep it open, atmosphere will take off the extra heat. Let it become 30 degree room temperature. Suddenly you want to go out somewhere, I want to keep inside the fridge means, definitely it will become colder. But fridge compressor has to do more work. Performance, coefficient of performance, beta will be reduced. Because denominator is high. Denominator is high means total value will be less. So these are the 2 points I want to discuss in refrigeration cycle. Okay. Next topic we are going to do is Mayer's relation. That is relation between Cp and Cv. Specific heat capacity at constant pressure Cp, specific heat capacity at constant volume Cv. Connecting these two is called Mays relation. You consider a gas in the container. With a frictionless piston, pressure P, volume V, temperature T. Moment you supply some heat energy, I want to keep the volume constant. Then definitely pressure increases. Volume is constant, pressure increases. So V, temperature changes to T plus dt. Definitely pressure increases. Sir, when you supply some heat energy to the system, the gas undergoes some changes, which pushes the piston upwards. Then how can you keep volume constant? You keep a small slotted weight over this piston. Or you put some sand particles over it so that the piston will not be raised. Our aim is to keep volume constant, that's all. So when you keep volume constant, the gas is not doing any work at all. By first law of thermodynamics, Q is the amount of energy given to the system, which is the sum of change in internal energy and work done by the system. Here, at constant volume, work done is zero, no work. Therefore, Q is equal to du. What is work done or energy? I mean, what is work done or change in internal energy? Formula we have already learned. Mass, mu moles of a gas, molar specific heat. Mass of the gas molecule into specific heat capacity into difference in temperature. Difference in temperature is dT. Specific heat capacity is C. We are keeping volume constant, so we are putting here CV. Good. Equation 1. Now remove the slotted weights. You want to keep the pressure constant. To keep the pressure constant, remove the slotted weights. What will happen? Then the gas is waiting to push the piston upwards. So some work is said to be done. So now the heat energy is du plus work done. This is Q dash. You take this as W dash. You take this as W. No problem. Because energy, internal energy, here internal energy is different. So what is Q? Formula wise, first law of thermodynamics, the basic formula for specific capacity, mu mole of a gas into Cp. You are keeping the pressure constant into temperature dt. So this is the actual. Now the system is here. So pressure P, volume V plus dV changed. From here the volume increases dV, temperature increases T plus dV. When you increase the heat energy here, temperature changes, pressure becomes constant, but volume changes because volume changes means pressure is a constant. Pressure is a constant of constant volume means pressure is changing. So two different points we are discussing. Constant volume, constant pressure. So substitute here implies what will happen, ma? Q. What is Q? Mu Cp into dt is equal to du. What is du? Mu Cv into dt plus W. W we have to calculate. Work done by the system. Work done W is equal to pressure into volume. PV. Integral PV. No, sir. I will use the equation PV, general equation. Any general equation or work done by the gas, any system you take, basic formula is P into V. dW I want. It is not the W here, it is dW I want to do it, sir. dW. dW means W is P into V. dW means keeping pressure constant, change in volume, keeping volume constant, change in pressure. Differentiation. In our system, pressure is constant here. So work done by the system is PdV only. PdV becomes 0. Therefore, mu Cp into dt is equal to mu. Here mu will come. Here no mu, we will see. Mu into Cv dt plus Pdv. But Pv is equal to R mu RT. Pdv is equal to mu R dt. Therefore, mu Cp dt is equal to mu Cv dt plus Pdv is nothing but mu R dt. Everywhere mu dt cancels. Cp is equal to Cv plus R. Or Cp minus Cv is equal to R. This is Mayer's relation. Specific heat capacity at constant pressure is always greater than the specific heat capacity at constant volume, because Cp minus Cv is equal to R. R is a positive value, 8.31 universal gas constant, which is a positive value. That means Cp is greater than C. So this concept only we have learned. Gamma in Carnot engine we have learned. In refrigeration cycle we have discussed. Based on adiabatic process. Adiabatic process means what? PV power gamma is equal to constant. This gamma is nothing but Cp by Cv. Cp is greater than Cv. If simplify nearly 1.41 value you will. Correct, mark? So this is Mayer's relation. So today's class we have discussed Carnot engine working based on four different processes, four different stages of Carnot engine, which is a heat engine. And we have calculated the efficiency 1 minus TL by TH. And second topic we have discussed refrigeration cycle, which is inverse of Carnot engine or reverse of Carnot engine or heat engine. Coefficient of performance we have calculated, that is beta TL by TH minus TL. This is the work done. And finally, we have seen Mayer's relation. Cp minus Cv is equal to R. Okay. So we'll continue the next class about new topics. Thank you.